Welcome, geometry students, to Unit 1.3, Segments and Their Measures. You're hearing the voice of Mr. May, and I'll be walking you through this particular unit. As always, please make sure that you have your guided notes with you. We will be completing them as we move along. So without further ado, let's begin. Our learning targets for the day. Learning target number 1, if we look at what we are attempting to do, we are attempting to define line segments based on points and distance along a line. So now we are going to look at line segments not only based on the points that compose them, but also the distance. That leads into being able to use the distance formula. Now, the distance formula is a formula that you will be given and will help you in defining the points and distance along a line segment. So learning targets 1 and 2 will work together. And then finally, we're going to learn how to use the segment addition postulate. The segment addition postulate, again, we are going to need to, first of all, learn the terminology associated with it, but then further than that, be able to use it when working with, as the name implies, segments. So our definitions. Our first definition is for a postulate, and postulates are rules. So it's a rule, but it is a rule that we accept without proof. You do not have to prove a postulate. It is somewhat common sense. It's something that is very straightforward, that you don't have to go through the process of really demonstrating why the particular postulate is true or why it works. It's something that when you immediately approach it, it becomes apparent and obvious why we can accept it without proof. And so a postulate we can accept as is. That is unlike a lot of things in geometry. In geometry, most of the examples that we work with will have to be proven. We will have to be able to show why a particular rule works or why it's true. But a postulate is one of those exceptions that we can just accept without having to prove. On the other hand, we have a theorem. And a theorem is also a rule. So it is also a rule. But these rules are proven. You have to show why it is true, why we can use that rule. It's not something that is immediately apparent. It is something that you may have to go through a couple of steps to say, okay, this works. And not only does it work in one case, it works in every single instance that we can show for this particular theorem. Now, you will experience both postulates and theorems throughout geometry. These are very important terms to remember because we are going to use them each. Because once you prove a theorem, you can use it then to solve problems or even prove other theorems or diagrams or examples or problems. So lots of different uses for theorems. Postulates, since we don't have to initially prove it, we can use that in the proof of other rules that we may be working with or other problems that we will be working with. So the two things you need to remember. With a postulate, you need to remember that it's a rule and it's without proof. And a theorem, it's also a rule, but it has to be proven. They are proven. Changing gears just a little bit to discuss congruent segments. So to discuss congruent segments. Now the first word that I want to focus on here is going to be congruent. Congruent means the same, okay? Congruent and same are synonymous terms in geometry. We do not use equal, only use equal or the equal sign when using numbers or measurements in geometry. Okay? So with geometry, we only use equal when using numbers or measurements. We use the term congruent. We use the term congruent to refer to the actual diagrams of the segments themselves that have the same length. So for example, if I were to draw two segments, and we'll say from A to B, remember segments have endpoints, so A to B, and I'm going to attempt to make these similar, the same distance. We'll call this segment X, Y, and I'm going to give you the information that AB, segment AB, is congruent or the same length to XY. Okay, so I'm referring to the segment itself. Now, if I want to write this in a notation that shows that they are congruent segments, first of all, we have to write our segment names. And if you recall from Unit 1.2, a segment has the 2 points, endpoints in its name, with the endpoints in the mathematical notation. And then we have a second segment, XY, and we're going to denote it as a segment using our segment notation. And then the symbol for congruent looks a lot like an equal sign, except it has the little, I think that's a tilde is what that's actually called, over top of it. So that is our same notation, or that is the mathematical way, symbol that we use for congruent. And so when I read this particular statement here, I would say segment AB is congruent to segment XY, which means that when I look back at them, when I look at these two segments, I know that the segments themselves, the actual diagrams of them, are the same length. So congruent means same. That is very, very important. Congruent means same. Okay? So congruent segments are the same length. I'm going to say that over and over again. That will recur throughout geometry. Ruler postulate. So a postulate, as you may recall, postulate does not, so this is without proof. Okay, so we do not have to prove a postulate. So the ruler postulate states that if I have a ruler, so if I were to pick up a ruler and set it down on this page, and I'll just kind of draw an example of a ruler, and rulers usually have marks, and then it's a longer mark that might be 1 inch or whatever the scale might be, and then you get 2 and 3 and so on and so forth. What the ruler postulate states is that if I have a line or a line segment, I can match them to points on a ruler. And that's where it says 1-to-1 with real numbers, okay? And so the real number will correspond to a coordinate point. So if I were to draw a segment, and I were to draw it from here to here, and I were to once again give this segment a name, then I can see that any point along this line is going to correspond to a real number that is on the ruler that I drew on this, just to give a visual example of what the ruler postulate says. So any point on this segment AB, and I could even extend it if I wanted to. I could make it a line, and I would make it a line by using the arrows. Remember, the arrows denote that it's a line, so it would go in all directions forever, or two directions forever, I'm sorry. And we could, once again, we could associate any point on that line with a point on the ruler, or more importantly, a real number on that ruler. So that is the ruler postulate. Basically says that any point on that line, that we can associate it with a number. One other thing that I want to remind you of, and this is from algebra. We are also going to begin working with distance. So the distance. Remember that distances are always positive. Distance is always positive. So if I look at the distance from A to B, it will be a positive number, just the same as the distance from B to A. Even though I'm going in a different direction, the distance will still be positive. And so that is what we mean with the terminology of absolute value. The absolute value of the distance from A to B basically says that the distance from A to B will always be positive. So that is the ruler postulate. And again, a postulate can be accepted without proof. So the segment addition postulate. So once again, we have a postulate, meaning that it can be accepted without proof. We're also working with segments, and if you recall from Unit 1.2, segments have a beginning, or actually have endpoints, and we could name them whatever we might choose. They have endpoints. And so the segment addition postulate, as the name might imply, is actually working with the operation of addition. And so what this is actually saying is that if I were to have a segment, and this segment had the point B, okay, and that point B is between points A and C, okay, then the A plus B, then what we can do is to get the full length of the segment, we can actually take the length of A to B, and let's make that yellow, the length of A to B, and we can add that to the length from B to C, and it will equal the entire length. And so, for example, and I'm just going to give you numbers for an example. If I were to say the distance, remember distance is always positive, if I were to say the distance from A to B is 4, and the distance from B to C is 5, then what you could determine from the segment addition postulate is that the total length from A to C would equal 9, because we would take the 4, add the 5, and it would equal 9. And so in this case, if I were to draw it down here, and I were to say this is A and this is B, then what it would look like is 4 plus 5 equals the total distance of 9. Okay, so we're just taking the two segments, the two smaller segments, adding them together to equal the larger segment. And so then what we can also say is go the other direction. If I'm given the information that AB plus BC is equal to AC, then I can also come to the conclusion that if I wanted to draw this diagram, then I would know that B, okay, the B is going to be the point in the middle. And let me keep with the same color scheme that I've been working with. I would know that B is in the middle between A and C. And so once again, this is the segment addition postulate. We're dealing with segments, which means they have endpoints. They do not go on forever. We are adding parts of segments or smaller portions of segments to equal the larger segment. And then it's a postulate, meaning that we can accept it without proof. And if you really step back and think about it from a larger picture perspective, it really does make sense that if I take a smaller portion, 4, for example, and I were to add it to another portion, 5, that is in a segment, that they would combine to equal the large segment as a whole, which would be the 9. That just seems to make sense, and that's why a postulate can be accepted without proof. It just makes sense. So, looks like we have a duplicate of the segment addition postulate. We've already covered that. So we're going to move on to the next, example number 1. So example number 1 is asking us to draw a sketch. And this is going back to our terminology from Unit 1.2. Again, the important thing about geometry, the terminology and vocabulary carries through to every single lesson. So collinear points. So I need to draw a sketch of 3 collinear points. Well, that brings up the terminology. What does collinear mean? Well, you may remember the hint is in the word. And so if I were to erase part of the highlight, the word that ends up is line, and then we talked about co, meaning together, like co-captains. And so what we have are 3 points in this case. We're working with 3. We're given a specific number. 3 points that are on the same line. So all I need to do is draw a sketch of 3 collinear points. Okay, and I can name them whatever I would like. It doesn't give me a specific name that I have to call them. So I'm going to call this X, this Y, and this Z. So there's point X, point Y, point Z. They're collinear. They're on the same line or line segment in this case. And so there's my labels. I've labeled them successfully. So my labels. Okay, so there's my labels. Now I need to write the segment addition postulate. Well, the segment addition postulate states that if I take the 2 smaller or parts of a line and add them together, I get the whole line or line segment. More importantly, line segment, because we're dealing with segment. We're dealing with the segment addition postulate. There's also another hint. The hint is we are going to add. So we're going to add segments. The hint is in the name. So what segments do we have? Well, we know that we have segment XY as a small segment, and I have to show that it's a segment. So I need to make sure that I use my segment notation. And I know that I'm going to add that to something. Well, what's my other small segment? Well, my other small segment is YZ. And again, I have to use my segment notation. And what will that equal? Well, it's got to equal the largest segment, which the largest segment is the entire segment XZ. And so what I have written is a very straightforward postulate, segment addition postulate, that describes the relationship between these 3 segments. And so what we have is we have XY added to YZ equals the entire segment XZ. So 3 collinear points labeled and written in such a way to show the segment addition postulate for the points on the segments. Example number 2. So in the diagram of collinear points, and so one thing that I need to begin with these collinear points is we need to do a quick correction just because they're a little bit off on the PowerPoint. Let's move them over a little, and this is going to be B and this will be C. Okay, so there's the 3 collinear points. Remember the word line. So we're dealing with a line or line segment. We know that BC is equal to 5. Well, where's BC? Well, we're dealing with this portion of the segment here, and we know that it is a distance of 5. We also know that BC is equal to. Now, why can I use equal to? Why can I use that? Because I'm dealing with a measure. That measure is 5. Well, AB, so we have BC, and it is 5. We have AB, okay, and it is equal, because we're dealing with a measure, it's equal to BC. So I can come over here, and I can label AB as 5. And so now I can find the following lengths. Well, AC is equal to, using the segment addition postulate, AB plus BC, which is equal to 5 plus 5, which is equal to 10. And then we already have the measure of AB because it is equal to BC, and that is 5. We're simply using the segment addition postulate with, instead of using the segment names, we're actually using the segment measures. And using measures, that is why we can use an equal sign. And so AC is equal to 10, and AB is equal to 5. Example number 3. So in the diagram of collinear points, so once again, we just need to probably move these to where they're a little, let me label them before I erase. So we have H, we have I, we have J, and K. And so let's get rid of these just so it looks better. Okay, so we have collinear points on the same line. We know that HK, so the entire distance, and so to show this, I'm actually going to do this and label it as 9. The entire distance is 9. We also know that HI is equal to JK, so we know that, let's go, HI is equal to JK. Okay, so those are going to be the same length. And then we also know that IJ, yellow, is equal to 1. So let's go ahead and label this as 1. Now we know we're going to use the segment addition postulate, okay? So let's go ahead and we're going to write segment addition postulate. So since we know we're going to use segment addition postulate, we need to write some sort of equation to show the relationships between these segments. And so what can we say using this segment addition postulate? Well, we know that the largest segment is HK, and that HK is going to be composed of the 3 smaller segments added together. Well, my 3 smaller segments are going to be HI. We're going to add that to IJ and also to segment JK. And just to keep with appropriate mathematical notation, I'm going to add the segment notations. And then to give you the color scheme, there's segment IJ, here's segment HK, JK, and HI. Now let's label the information that we have. So now we can substitute in the values. So HK, we know is a value of 9. We've been given that. We also know that the value of IJ is 1, but that leaves us wondering what is HI and what is JK. Well, anytime in math we don't know the value of something, we represent it with the variable. And so let's call hi, we could choose any variable we want, and I'm actually going to change that color. Let's go with calling it x. Okay, x represents an unknown value. And so if I call hi x, we also know from what's given that hi is equal to the value of jk, so we can also call jk x. So now, and let's put back our color scheme real quick. jk and hk and finally ij. So now we have an equation, and this is an equation that we can now solve using just our algebraic rules of combining like terms and solving for the variable. So my like terms, so I have two like terms, which I'm going to, my x and my x, so I can combine those to end up with 2x. The 1 I will leave by itself, and then it is equal to 9. To isolate the x, I'm going to subtract 1 from both sides, because if I do something on one side of the equation, I also have to do it to the other. And I end up with 2x equals 8. And I'm going to move that up here just so I'll rewrite it. 2x equals 8. And now this is an implied multiplication, and in order to, the inverse operation is a division. So I'm going to divide by 2. And so my x is now equal to 4. And so now that I've solved for x, I can look and I can find these following values. Well, hi, we know that hi is the segment that we called x, and we know that x is equal to 4, so hi is equal to 4. We know that hi is equal to jk, so that we know that it is also 4. hj is the segment hi plus, okay, so segment hi plus segment ij. So that means that hi is 4 plus 1, which is 5. And then ik is going to be the same type of operation. It's going to be ij plus jk. And so that is going to equal 1 plus 4, which is equal to 5. And so now we have found the values of all of the lengths of these segments. And we used the segment addition postulate in order to set up an equation that allows us to solve for the missing variable. And again, anytime there is a missing value, we are going to assign it a variable. And in this case, we assigned it the variable x. So working example number 4. Example number 4 is once again an example of the segment addition postulate. So I will begin by drawing the segment, and then I want you to hit pause and work it yourself. We will end the video there, and then in class you will have the opportunity to go over it in your group or with your teacher. So let's draw the diagram. So suppose that J is between H and K. So we have to draw a segment. So we have our segment, and we know that J is between H and K. So that is this portion of the question. So now we're going to use the segment addition postulate to solve for x and then find the length of each segment. So go ahead and pause, see if you can work it. And I'll go ahead, once you're back, I'm going to set up this equation. So HJ is this portion of the segment here. And we know that HJ has the value of 3x plus 8. We know that JK is this portion of the segment and has the value of 2x minus 5. And then the entire segment is a value of 23. And so using the segment addition postulate, what is going to happen is we are going to take the first portion, 3x plus 8, plus, okay, because we're taking the pink portion and the green portion, the two smaller segments, and we're going to add them, and I'm going to put them in parentheses because they are expressions, and those are going to equal the total of 23. Now, because this is a plus, I can drop the parentheses in the second parentheses. Actually, I could drop all the parentheses. And when I rewrite that, I can rewrite it as 3x plus 8 plus 2x minus 5 equals 23. Looking at like terms, I know that these are my like terms, and I also know that these are like terms, so I could combine my like terms, and I will have 5x minus, or plus, I'm sorry, plus 3 plus 8 and minus 5 is a plus 3 equals 23. From this point, we use algebra in order to solve, and when I solve for x, I end up with x equals 4. And the way that I get there is I subtract the 3 from both sides, and I get 5x equals 20, and then I divide both sides by 5. 20 divided by 5 is 4. And now when I find the length of each segment, what I need to do is I need to substitute the 4 back in, because it's asking for the length of each segment. So now 3 times 4 is 12. 12 plus 8 is 20. 2 times 4 minus 5. So 2 times 4 is 8. 8 minus 5 is equal to 3. And then KH, the entire segment, is 23. Now, if we did it correctly, 20 plus 3, 20 plus 3, okay, I'm looking right through here, 20 plus 3, that is equal to 23. Therefore, our segment addition postulate is true. So with that, this is the conclusion of our notes. As always, make sure that you review them. If you have any questions, please contact a teacher or math teacher. We'll be more than happy to help you with it. And as always, we look forward to seeing you in class.